Hi, everyone. Welcome back to Google I/O. Hope you had a good time yesterday. Hope you have a good day today. I'm Dan Bornstein. I'm here to tell you about the Dalvik virtual machine. So a little bit about my background. I joined Google in 2005 to work on the Android project, and I've been working on Dalvik almost the entire time. Before Google, I worked on a couple different VMs at a few different companies, including on the HipTop virtual machine immediately prior to Google. And although I did start the Dalvik project at Google, the virtual machine and the libraries wouldn't be where they are today without the work of a whole lot of other people, about half a dozen core contributors and a slew of other help throughout the team. So thanks to those guys. If you're curious about the name, Dalvik, Iceland is in the northern part of the country, northern part of Iceland. If you want to go to the Arctic Circle, you can catch a ferry there. So. Okay, if you're familiar with Android at all, you've probably seen this diagram. Very briefly, Android is it's a new platform for mobile devices, and it really is the complete stack. It includes layers from the OS kernel at the bottom and drivers up through an application framework at the top, and it even includes a few applications. You write your applications in the Java programming language, and they get translated after compilation into a form that runs on the Dalvik virtual machine. And the rest of this talk is really just about the virtual machine. I'm going to give you a tour of a couple aspects of the VM's design, and in particular how it was influenced by the constraints imposed by the rest of the platform. And at the end, I'm going to distill out just a couple pieces of advice for your application development on this platform. I'm going to assume you're generally familiar with the Java programming language and know at least a little bit about what it means to be a virtual machine. And if I omit a few details, I'm going to try to leave plenty of time for Q&A at the end. So just be aware of that, and just hold your questions, and I will try to answer anything you have after the talk. So the virtual machine, again, is designed based on the constraints of the platform. And you can see a few of the key ones. We're assuming not a particularly powerful CPU, not very much RAM, especially by, say, today's desktop standards. An easy way to think about it is as approximately equivalent to like a late 90s desktop machine with a little more modern operating system, but with one very important constraint. So batteries are getting better as time goes on, just like any technology. Unfortunately, it doesn't look like it's keeping up with Moore's law. So 18 months, your CPUs are getting faster, your memory density is getting twice as much, but your battery life isn't quite keeping up. So that really is a key concern for any kind of mobile development. So now that you know a little bit about our constraints, let's see how we address a couple of them. As I said, we're expecting to run on fairly low memory devices by desktop standards. So in particular, this is kind of how a low-end Android device is going to look in terms of system characteristics. So once everything is started up on the system, we're not really expecting there to be that much memory left for applications. And of course, so we try to make the most of that. But one wrinkle in the works is that the Android platform security relies on modern process separation. So each application is running in a separate process. There's a separate address space. It has separate memory. And apps are not allowed to interfere with each other at that level. And so that means that unless you do something special, that 20 megs really isn't going to go far at all. And in addition, a modern platform that we try to make it, have a rich set of APIs for developers to use, we have a fairly large system library. And so, again, if you don't do anything special, well, with a 10 meg library, 20 megs left for apps, that really, really doesn't leave much space at all. And I think I had a previous slide. We don't have swap space, so just want to emphasize that. So there's no, if you have 64 megs of RAM, you have 64 megs of RAM, and that's kind of the size of it. Okay. So as I said, we translate Java.class files into a new form to execute on the device. That form is called a DEX file. It stands for Dalvik executable. And here is, in a very general way, what a DEX file looks like. The sizes of those areas aren't to scale, but it's meant to give you at least a general impression. After the header, there are these 5 separate constant pool sections. Each constant pool section is of a particular type. You can see what they are there. Just for example, at the top there, the string IDs section identifies literally strings. So any string that you have in your file, be it in your code, either an explicit quoted string in the source or, say, the name of a method, name of a field, those will all end up having references in the string IDs section. And then towards the bottom, there are a series of class definitions. So a DEX file contains multiple classes. Each one of those has a little section there. And then at the bottom, there's general data. So all of these other sections will end up pointing at that data. And actually, the sections will point back and forth at each other. So for example, a type ID, so this is something that names a type, such as a class or a primitive type. Well, the name of that is represented in the strings. A method has a name and a signature, and you can see how those point around. As I said, there's a build time tool that does this translation. So this is just a simple illustration of how, say, several classes in a .jar file turn into a single DEX file. Okay, and this is just a few classes I'm going to use as an example. So there's a interface, an implementer of that interface, and use of that implemented interface. Here is approximately what that looks like as separate .class files. This is a very oversimplified diagram, but again, it's meant to give you a flavor of the strings in those files and the various references. And you can see that there's a fair amount of duplication. What I'm pointing at here are the method signatures. So each one of these classes refers to a method which takes the same arguments and the same return type. And so each one of those classes is going to have that full signature there. And in addition, there's a fair amount of strings that label internal bits of the class files themselves. On the other hand, this is what it looks like as a DEX file. Again, we've collapsed all of those the separate constant pools into one constant pool. And as a result, there's a bit more pointing around inside a DEX file. But as a result, we get to share a lot more. So you can see that there are many fewer boxes in this diagram than there were in the previous one. And that really does represent that there's less total storage required for this shared constant pool in a DEX. So the point here, again, is that sharing these separately typed constant pools among all of the classes, it's reducing the amount of data that you need to represent all of them together. And in addition to this sharing just at the constant pool level, we were fairly careful about how we lay out all of the structures in the file. And I'm not going to talk about that more, but I'd be happy to answer questions later about that. But I wanted to just show you kind of the high-level conclusion. So these numbers are sizes in bytes of the system libraries of the Android platform, along with a couple of sample applications. I took these numbers about 2 weeks ago, so they're reasonably accurate. So what you can see there is that a normal jar file is generally about half the size of the uncompressed class files. And at the same time, the uncompressed DEX file that represents the exact same code is usually a couple percentage points even smaller than that compressed jar file. And you may be wondering why we care so much about having these good uncompressed characteristics. Well, so here's why. So on really any modern operating system, you can think of there as being 4 different kinds of memory in a very general sense. And that's 2 variants along on sort of 2 axes. There's clean memory versus dirty memory, and there's shared memory versus private memory. Clean memory is simply any memory that the operating system kernel can drop from main memory and not have any impact on the overall semantics of the system. And the reason it can drop it is either because it is, say, just a page full of zeros, and the kernel knows that, oh, if it's zeros, I can recreate a page of zeros on demand. And similarly, if it's backed by a file, you can map in those pages from the file again as you need to on demand. Shared versus private. Private memory is simply memory that is used only by one process, and shared memory is memory that's used by multiple processes. As I said, clean memory is ideal because the kernel can just eject those pages from RAM pretty much at will. And shared is better because any cost of that memory that is going to have to stay in main memory until it gets freed, that cost is at least amortized across multiple processes. So shared clean is even better than private clean, but either kind of clean memory is good. Private dirty is the kind of memory that we want to minimize. So on the Android platform, this is kind of how it shakes up. As clean memory, these uncompressed DEX files get mapped in. And these are either the system library, obviously, and also any application DEX file. These all get to be mapped into memory. And private dirty memory is any of the associated structures once you start up the virtual machine. When you load a class, when you refer to methods, these require some amount of live dirty memory to represent, as well as the general application heap. When you construct objects, they have to go into memory, and that becomes dirty memory. For any given application, it's going to have some code, generally going to have some code that is private to it. It's going to have its own heap. So these are going to be private memory, private dirty memory. And the important question is, what can we do to have shared dirty memory? And our solution to that is this thing that we call the Zygote. What we do with the Zygote, as its name implies, it comes into existence fairly early on during the boot of an Android system. And its job is to load up those classes that we believe will be used across many applications. So it goes and creates a heap. It goes and creates that dirty memory to represent those classes and methods. And then it sort of sits on a socket and it waits for commands. And when it gets a command to start up a new application, it does a normal Unix fork, and then that child process becomes that target application. And the result of that is this. So the Zygote, again, has made this heap of objects. It's made this live DEX structures. And then each application that then starts up, instead of having its own memory for those things, it just shares it with the Zygote and also with any other app that's also on the system. So back to that slide. This answers the question. So our goal, again, is to get as much memory to be mapped clean as possible. But we at least have this out for where we really do have to allocate, that we can reduce the cost in terms of the whole system performance. So garbage collection actually throws a little bit of a wrinkle into things. In general, there are two strategies for how one represents the meta information that you need when doing a garbage collection. On the left, you can see one style is you have this associated information, say mark bits, sitting next to each object that's allocated, so that when you do a garbage collection, that data is right there. So if you're going to scan an object, you'll have the mark bits right there ready to go. On the other hand, you can keep all the kind of the live object data together and have this separate allocation for your garbage collection information. And the argument can really go either way, at least in the larger sense. For like on the one hand, if you have the mark bits embedded with the object, well, that means that when you're garbage collecting, the cache lines for that object will already be warm by the time you need to scan the object. On the other hand, you have better when you're not garbage collecting. If you keep the garbage collection information separately, when you're not collecting, then you have a more dense cache. So that's the big picture. However, again, with the Android platform, we do always have to keep in mind that we are trying to exist in a world where there are these multiple processes all living on a fairly constrained device. And they are separate processes. Each process has a separate heap. Each heap is garbage collected independently. And that really led us to the conclusion that for Android at least, having the separate garbage collection information, having mark bits be separate, is the only viable solution. And this is particularly true because of that Zygote process. Remember, the Zygote has its own heap, and that heap is shared. So if we had mark bits interspersed in that Zygote heap, the moment that we did a garbage collect, the process would try to touch those pages in the Zygote and therefore force them to be unshared. So we would very quickly find that instead of having shared dirty memory, we would have private dirty memory, and that would kill the memory performance on the system. And I should add, one additional benefit is because most processes aren't garbage collecting most of the time, we don't actually have to allocate that mark array except during those moments when we're doing the garbage collect. And again, that means that there's that much more memory for additional apps to be running simultaneously. Okay, now I just want to take a few minutes to tell you what we do on the CPU front. Again, as I said at the beginning, we're running on a platform, or expecting to run on a platform that looks like what you might have had on your desktop 10 years ago. And you can see that it's a fairly slow bus, almost no data cache at all. And I just want to reemphasize that there's very little RAM for applications once you consider all of the things that your device is doing, say, as a phone. It has to answer phone calls. It has to be able to take in, send SMSs. All of these things are essential services as far as the user is concerned. So before I tell you what we are doing to address these, I'm going to tell you one thing that we're not doing, at least in the 1.0 timeframe. So we're not doing a just-in-time compiler. And the reason we don't is it gets right back to that memory issue. When you compile code from a bytecode to assembly, that's typically going to make the code grow at least a bit. Unless you're doing something fairly clever, you're not going to be you'll be using dirty memory for that JIT cache. So that again increases the memory pressure. And in addition, if you look at the big picture of the system, we're providing a lot of native code to do the really heavy lifting. So to do the 2D and the 3D graphics, to do audio and video. So we provide native libraries for all of those things. So the interpreter performance or the high-level language performance really doesn't come into play for at least a large class of things that you'll be doing a lot of the time. And if you're a platform developer as opposed to an app developer, you can always add new functionality that you need via JNI. So the short version really is you can always imagine an application that you would want to write that could use just a little bit more CPU efficiency. However, there are plenty of apps that will do just fine, and generally, just with a little careful coding, you can really mitigate any negative effects that there otherwise would have been. And I'll talk a little bit about that later. So what are we doing to actually be efficient on the platform? So first of all, when an application gets installed, and also when the system itself gets installed, the system will do a lot of work up front to avoid doing work at runtime. So one of the major things we do is verification of DEX files. And what this means is that as a type-safe, reference-safe runtime, we want to ensure that the code that we're running doesn't violate the constraints of the system. It doesn't violate type safety, doesn't violate reference safety. And for Android, this is really more about minimizing the impact of bugs in an application as opposed to being a security consideration in and of itself. Again, this is because for Android, the platform security is really being guarded by the process boundaries as opposed to anything that we're doing within a single process. Although this is at least a little bit of a concern for our more sensitive, say, system processes, where we really want to try to guard against bugs because those bugs could turn into security violations. In addition to verification, we do optimization. And so the first time that a DEX file lands on a device, we do that verification work. We also augment that file. If we have to, we will do byte swapping and pad out structures. And in addition, we have a bunch of other things that we do such that when it comes time to run, we can run that much faster. So as an example of static linking, when a DEX file arrives on a device, it will have symbolic references to methods and fields. But afterwards, it might just be a simple integer vtable offset, so that for invoking a method, instead of having to do, say, a string-based lookup, it can just simply index into a vtable. And just as another example, you are probably aware that the constructor for java.lang.object does nothing inside it, and the system can tell. So instead of actually doing that anytime you're constructing an object, we know to avoid just making that call, and that actually does make a significant performance impact. The most radical thing that we do in DEX files is to have an entirely new bytecode instruction set. DEX bytecode is defined in terms of an infinite register machine with no intra-frame stack. So there's a normal machine stack in terms of one method calling another, but within a method, it's all just registers. And we chose this because it lets us have a very efficient interpreter because each instruction that we interpret is semantically more dense. And I'll show an example of that in a couple slides. So here's a couple statistics. This is just a general expectation, what you can find when you're converting a set of .class files into a DEX file. We have fewer instructions, and we have fewer code units, and I'll talk about that in a second. But we do have more bytes, and the distinction here is that a code unit in a .class file is a single byte, and a code unit in DEX is 2 bytes. And in the interpreter itself, we can issue reads to read those pairs of bytes at a time. And so that helps mitigate the impact of having more bytes typically. And now I'm just going to go walk through a couple of actual examples. These are all real. I used the real tools on our device to compile these and dump the results. So no hand waving, at least, for the next few slides. So this is just a short, but I hope realistic method so that we can compare the various bytecode. And this is simply adding up the contents of an array and returning that value. So this is what it looks like as a .class file, or the bytecode of a .class file. And I've highlighted the loop in red, and I've annotated it so that you can see what each instruction is doing in terms of reading or writing a local variable or a stack location. And you can see the summary stats up at the top right. Those 45 reads are really 25 byte reads to read those instructions in, 12 reads of the stack, 8 reads of the local, so that's all 45. Similarly, you can break down the writes. And this is, I should say, those stats are for effectively a naive interpreter. And you can save a bit if you're a little more clever. You can probably save at least six reads, at least 6 writes with a fancier interpreter. But that gives you a general picture. Here's what it looks like as a DEX file. So you can see there's many fewer bytes, many fewer instruction dispatches, less than half the number of reads and writes. And I should add, instruction dispatch is one of the big killers of interpreter performance. So it really helps to be able to dispatch fewer opcodes especially in your inner loops. Okay. So sometimes you really need to have just a big array of data. And if you've ever looked at what something like this looks like in a .class file, it's not pretty. So this really is the code that's needed to initialize that previous array. It's 44 bytes of instructions, another 35 bytes in the constant pool, and it's 4 instruction dispatches just to initialize each element. And each time you add another element to, say, an int array, it's 11 bytes of code and constant combined, and another 4 instruction dispatches. So a lot of people are aware of this particular problem, and there's a standard workaround for that. So here you can see that what we're doing is representing that int data instead as a string, because strings are a little more compactly represented in a .class file. Unfortunately, this still has a couple of problems. One is that in order to decode that string, you have to have a bit of code in a loop, and it's going to end up doing even more work than the original version that I showed. And in addition, that string is represented less than ideally in a .class file because it's encoded as UTF-8. Each one of those characters really will turn into 3 bytes. So you still have some expansion compared to your original data. So knowing that, this is what we do in a DEX file. This is the same code, which has been translated into a .dex file. You can see that in this case, we're only using 46 bytes for this example. And as you add elements to that int array, it's just 4 more bytes per element, which is exactly the data represented. And we only have to interpret one opcode to do that entire initialization. And that's the third one down, the fill array data. As I said, if we wanted to add, say, 6 more elements, it's really just adding the 6 more elements worth of data. And this is both a speed and a space efficiency win. Measured on our system libraries, it saves us something like 100K. Oh, and just wanted to mention, if you look at number 9 there, the no-op, we do that so that the array data itself is aligned on an int boundary, and that makes reading that data a little more efficient in the interpreter. Ask that question during Q&A. I'll get to it. OK, I'm going to give you a very brief introduction to how bytecode interpreters are put together. This is just a toy interpreter. I will give you exactly one guess about the output of this program. You can imagine that instead of consuming characters from a string, each one of those characters could be a complex opcode with a non-trivial implementation. And this is a perfectly reasonable way to put together an interpreter if performance is not a consideration. And the big problem with this is there's a lot of excess branching. So with that outer for loop, at the end of each opcode, you're branching back from the bottom of the loop back to the top. Within each opcode, at the end of it, you're branching to the bottom. Again, at the top of the loop, you're branching into an opcode. There's something like 4 branches just to do one opcode. So the fine folks who put together the GCC compiler are very aware of this problem, and there's a great extension to the C language that helps with it. And it's called computed goto. So this is one case where goto really isn't evil. So in this case, instead of having an explicit loop and an explicit switch statement, we build in that switch into each opcode, so that when you're done interpreting one opcode, you immediately can load up the next opcode and branch to it directly. So just one branch per opcode. So here's where this toy example will break down a little bit. But suffice it to say that there are still cases where a human can do better than a compiler at things like register allocation and laying out some data structures. So it's possible to write effectively the same technique as that last one in assembly. So here you can see I've elided a lot of the details, but the dispatch I've fully written out. You can see there's still two reads of memory to do that dispatch. The first read is reading from your interpreted program counter, and the second read is reading from your opcode table to find the address of that next opcode. So as I've implied before at least, any memory activity that you have is going to be a significant performance impact. So if you can get rid of a read, you're doing pretty good. And that's exactly what we do. So instead of having that second memory read, what we do is have the base address of the entire interpreter sitting in a register, and we guarantee that each opcode takes up the exact same number of bytes. So we will pad it if an opcode happens to be short. There are a few of those. We won't use the entire space allocated for that opcode. And similarly, or if a opcode happens to be one of the more heavier weight ones, such as a method invocation or field access, stuff like that, we will branch off to a helper function. But what that means, so there's really two benefits here. One is, again, we're avoiding that dispatch. And another one is that we get to align the implementation of each opcode on a cache line boundary. So if there is an opcode which doesn't happen to be used a lot, it won't be taking up any space in the cache, and that helps with leaving space for any other data accesses that your code might want to do. So now that you know a little bit more about how the VM is put together, I just want to take a couple minutes to talk about how you can optimize your code for Dalvik, or really for mobile devices in general. Again, the really big difference is the battery. So if you do anything, I mean, if your code does anything, this means that your code is consuming milliwatts, and those milliwatts have to come from somewhere. That somewhere is the battery. Again, battery technology keeps getting better, but if it's not plugged into the wall, it's gonna run out eventually. So I tend to think of the optimization problem in terms of timescales. So there's human timescale versus computer timescale. On the human side, there's human interaction is, say, a fast typist who can type at, let's say, 10 characters per second or so. If you're dragging a mouse or doing a finger gesture, say 15 to 30 points per second is really about what you need to register. On the perception scale, that's more like if you're listening to audio or watching video, you'll have to have, say, 25 to 30 frames per second, and you'll want continuous audio that's reasonably synchronized. At the computer scale, this is when you're doing some computation and you're just computing all out, and it doesn't matter what the user is interested in. The computer just needs to crank through. And the optimization problem is really a matter of trying to avoid having to do computer scale computations. So, at computer scale, that's when you're really eating through the battery. And if your code really has to run at computer scale, any optimization that you do that doesn't sort of bring you up to one of the other scales it's sort of prolonging the agony before death. So with that, my first advice for well-behaved applications is to get plenty of rest. So a good app is one that's sitting and patiently waiting for user input, for network input. And when that input comes in, it looks at that input, it reacts to it, and then just goes back to sleep. So for example, as you're typing on a keyboard, you get that key input, and you want to react to it. You want to, display that character, move the cursor forward, and then again go back to sleep. And help that cursor. That's just an animation, and so it should be sleeping, say, for a half a second, and redrawing the next one, sleeping a half a second. Again, you add it up. Hopefully, you end up sleeping most of the time, and that helps prolong your battery life. But sometimes you do have to have a loop, and sometimes it really does have to operate, at least briefly, on computer scale. And so with that, my advice is to loop wisely. This is just 7 typical headers of a for loop. I've arranged them approximately in order from most efficient to least efficient. And I should just add as a caveat, really, unless you're operating at computer scale, this advice doesn't matter. So the first 3 of those are all about in the same territory of efficiency. But the first one, you can see, seems a little unnatural, at least in many circumstances. So I wouldn't go crazy sort of making all your loops count down unless it really makes sense for the code. So I would really advise, if you can manage to fit your loop into one of those 2, then you're doing pretty good. However, if you find that you have to do a lot of generic object-based iterators at computer scale, then you have a problem. And it's generally a solvable problem, but just be aware that if you find yourself doing that, that you should probably try to find a different way to help give your user a little more battery. So especially because making an iterator, it's going to do an object allocation. And if you keep on allocating objects at computer scale, that means you're garbage collecting at computer scale. And GCs, although aren't too bad, if you do enough of them, they are going to impact your performance. And that really gets to my last piece of advice, which is just avoid allocation. And on the one hand, if you have short-lived objects, so for example, those iterators probably aren't each one isn't going to last too long, but they do need to get garbage collected, and garbage collection takes CPU time, takes energy. And on the other hand, if you have a long-lived object, well, that's dirty memory, and your user wants to do something else with that. They want to be able to run every app under the sun simultaneously, and the more long-lived allocation you have, the fewer apps that the user is actually going to be able to run. And I know this is a little bit of a bind. I'm saying don't allocate short, don't allocate long. Really, it boils down to be frugal in how you allocate. If you're allocating say a long-lived object, make sure that allocation is in support of operating at one of the human timescales as opposed to operating at one of the computer timescales. So that's the extent of my advice for you. And that's about all I have to tell you today. Oh. Thanks. As I said, the design was really a result of these system pressures, and we've done what we can to help minimize the pain for developers, but of course we can only go so far. So I hope that with this knowledge you can go and write even better applications for the platform and give the users' batteries a little bit of a break. So with that, I think we have a few minutes for questions, and I'd be happy to take them. Oh, and before we get started, I believe that you all have little cards for speaker evaluations. All of us would appreciate it if you would take a couple minutes to fill those out and tell us what we got right and what we got wrong. Okay, sir?
So you mentioned that the virtual machine was designed to be run on the 64 megabytes. Mm-hmm. Does that mean that everything won't exceed 64 megabytes?
So that 64 megabyte number is really, it's a design consideration for the software development work. So as a software developer on the Android project, my job is to put together the software. I don't put together the hardware. And from project perspective, we hope there to be a lot of pieces of hardware that run the Android platform. what we wanted to do was define kind of what the low end of what we expected to be able to run on, as opposed to saying it must be 64 megs. We're just saying we don't expect to run with fewer than 64 megs. If you have more than that, we are happy to have that extra memory to, again, run more applications, or eventually say, augment the system libraries with even more functionality. Oh, sure.
And from yesterday's session, that somebody mentioned that there is a low memory killer in the kernel.
Mm-hmm.
So how does it work with this Dalvik virtual machine?
So the low memory killer is part of the larger system design of Android. I'm no expert on it, but I can talk about it a little bit at least. As I said, we want to be able to run as many applications as the user wants to run, and the aim of the platform is to give the user the impression that all apps are always running. So if they switch to email, their email should just show up. If they switch to maps, say, the maps should just show up. Under the covers, however, if loading up the email application means that there's not enough memory not enough application memory to support all the simultaneous uses, the low memory killer will find the application that was, say, used least recently and kill it to make more memory, make more memory available for the processes that are actually active on the system.
Okay, so the bottom line is that we can have more hardware memory.
I'm sorry, say again?
So we can provide as many of hardware memory as possible,
mm-hmm.
but the low memory killer won't matter how the virtual machine work.
Yeah, the low memory killer really is it operates at the process level. So the low memory killer can kill a virtual machine just as easily as it could kill a program written in C or C++. Okay. Hi.
I have a question about your for loop example.
Oh, okay.
So certainly using the iterator is a bad thing just because of object creation and stuff like that. Mm-hmm. But is it really an issue in terms of the garbage collector? Like, are all objects always allocated on the heap, or are simple examples like that going to be on the stack?
No, actually, we do all allocation for the 1.0 version. All allocations are done on the heap.
Okay.
And so you say new something or other, or
mm-hmm.
code does it sort of under the covers for you. That really turns into a little piece of code on the heap.
Are there any plans to change that in the future, or is it not a big deal in most cases? Or?
So I think the very general answer is we always want to make it better.
Okay.
Offhand, I don't know whether doing stack allocation of that kind of object will turn into a net win for the platform. It very well might. Mm-hmm. We're actually just on the cusp of exploring what we want to do after 1.0.
Okay, thanks.
Mm-hmm. Oh, over here.
So you had a lot of examples of converting class files to DEX files, mm-hmm. and converting Java to Java bytecode to DEX.
Mm-hmm.
Is there any reason that you started with Java rather than, say, the common language or the CLR, or even writing a new compiler that goes directly from some language to DEX?
Yeah. Actually, I think I can answer the second ones with a more definitive answer. If you look at the sort of the ecology of computer systems, there's a lot of support for the Java programming language. So there's Eclipse, there's NetBeans, there's IntelliJ, there's Emacs support even. There's JDB. There's I happen to be fond of this debugger called JSWAT. And there's a lot of activity in terms of Java development, especially in the open source world. And when we were building this platform, we really didn't want to throw something totally new out there that was unfamiliar and didn't have rich tool support. And sort of we surveyed things, and it seemed like the local maximum really was supporting programming in the Java programming language, and again supporting the debuggers, the IDEs, and all that. In terms of CLR in particular versus Java, I'll have to say my impression is that there's more open source activity in the Java world. I don't know if that's strictly true or not, but it did seem like a reasonable choice. And I guess there was one last. You said compile some language, say, directly into some other language directly into the DEX format.
Yes.
Eventually that could happen. There's nothing that should keep anyone from being able to do that. However, there were already reasonable compilers for the programming language that we cared about. In fact, there are multiple compilers, and we will work with pretty much any of them. And in addition, there are other source languages that compile to .class files, and we can already take advantage of, or rather, the platform can already execute those by virtue of the translation from .class files. Whereas if we wrote a source compiler, we would only have that one source language.
Okay, thank you.
Over here.
My question is, what kind of Linux kernel are you running, and what modifications have you made for your environment?
Okay. I'm far from the best person to answer this. We are currently on the Linux 2.6 series. I don't remember which minor version 24. We're on. 24, someone said? Okay. See, we've actually published all of our modifications. So with the first SDK release, we also published a Git repository. I'm sure you can find a URL for it. It's, and I believe we push regular updates to it.
So the improvements you mentioned that you did to the class files to DEX, any improvements that you can actually push back to the bytecode, Java bytecode, or some tweaks that you found that you could actually push back to the Java world?
Well, the .class format is fairly well set in stone, so I don't know that there's much, say, direct influence that our work can have on the .class format. However, just as with the vast majority of the Android source code, all of this is going to get open sourced, and my hope is that this code, while it may not say, transfer into some other project directly, at least the ideas that we've explored can help inform other projects on their decisions for how they build similar systems.
Yeah, for example, just building a better J2ME, like a better mobile version of Java, something like that. And the second question is, it goes along the lines of previous. You can actually run Jython in.
So, I don't know about Jython in particular. There's one major thing that we don't support in the current incarnation, at least not directly, because our executable format isn't .class files. Once you're on a device, there's nothing to read a .class file. So I believe Jython will generate new class files on the fly. We don't currently have a mechanism for reading those .class files in and translating them on the fly into DEX files. So any language runtime that requires that isn't going to be able to operate on a Dalvik VM without having some major surgery done to it.
Yeah, thank you.
Hi. when you create an activity, a sort of activity, they make a little bit of a difference there in the SDK. I think one will translate to a fork, and the other one will translate to a VFork, or how it actually work internally? Like when you start a sub-activity as opposed to an activity. Like the Zygote, for example, you said that it will start the home screen, right? So it will start an activity very much, right? So the Zygote will fork the home APK.
So it's not so much, say, fork versus vfork. It's really whether you're within the same process or within a different process. And each, actually caveat, I'm also not the best person to answer this question, but I'll try to give it a go. Each intent that the system receives, it will try to figure out which APK is the best one to deal with it. If the kind of the application behind that hasn't yet been started, then the act of responding to that intent will cause a new process to come into existence.
And yeah, okay. Finally, like on Java, basically, when you implement a VM, basically, like you have a lot of native calls that you're currently executing on the phone. Some of those native calls are blocked, are blocking calls. And if, let's say, one of those calls blocks and the phone fails, the device pretty much, then you have like a watchdog timer reset or something of thing like that. How the Dalvik VM, or what do we need to do to get those not a blocking call, or do we need to implement some sort of timer task before we actually make the native call, or how will that work?
No, you don't generally have to worry about quite that level of detail. The way I would put it is that you want your user interface to be fairly responsive. So if you're going to do a blocking operation, especially one that's going to really block for, say, for seconds, you don't want to do that in your UI thread. You'd much rather do that, say, in a side thread.
Right. No, but what I'm saying is, like, the OS, I mean, the VM will be executing actually the native call. So the timer slice will belong to the native, right? So independently of what you have thread-wise on the VM, it doesn't matter because you're actually executing a native call.
So a native call is, from the system perspective, whether a call happens to be native or interpreted really doesn't make that much difference. It's really more about what thread is doing that, and in sort of which applications are being particularly active. So I thought your original question had to do about like not wanting to lock up the system. Was that
right? Like exactly, because when you're implemented on Java, let's say Java VM, you should have run into that specific problem.
So for us, this may be a little oversimplified, but our aim really is that if a process is misbehaving, it's really sort of limited to just that process having trouble and not affecting the rest of the system. So, for example, there are we define there to be, say, like physical buttons that aren't intercepted by or aren't interceptable by the application. So the easy example of that is like the send or the end button, the home button. So if you happen to be, as a user, you see this application, it's misbehaving, you should be able to like just hit the home key, and that app may continue to misbehave in the background, but then your home screen will come back up. You can do other stuff, and eventually, if it turns into a kind of system problem, that system process killer can go ahead and kill it.
So basically, we'll just trigger an interrupt, and that's actually hooked to the Dalvik VM, and it will.
Yeah, it's actually hooked at even lower a level than the VM itself.
Yeah, okay, thanks.
Okay, I think I have time for one more question.
Okay, good. This is a long one.
Uh-oh.
No. I was recently working on an example that needed to perform some image manipulation, and it had two nested do loops, going from 1 to 100, 1 to 100, and just a really simple piece of math in the middle. And I noticed that I could tell it was running it, depending on whether it was 100 or 200, it might take a second or so which is kind of long. First part is, how would I optimize that in Java so it would run fast on Dalvik? And the second part is, let's say there was a JNI call to do that. Have you done anything with optimizing the JNI calls to speed them up over straight JNI?
Well, actually, I think I only have time to answer half of that. I apologize. I'll answer the JNI question. So we support real JNI, and what we have done is a couple of tweaks to how we implement that to make it about as painless and efficient as a JNI call could possibly be. So in terms of application level code, that's about all we can do. In terms of the platform code, if you're a platform developer as opposed to an application developer, there is a way to do a native call that avoids a lot of the JNI overhead. However, for the sake of portability, we only expose that as kind of like a very low level platform feature. So with that, thank you very, very much for coming. And if you are interested in asking further questions, I will be at the Android booth out in the hall